All right. Hi, everyone. So, at least in the States, statisticians tend to have a reputation of, at least when I say what I do, people are like, oh, statistics. So now I feel like it's just appropriate that I'm what's standing between you guys and lunch. So, and I'd also say it's sort of like my class I've been teaching this semester to undergraduates, which is right before lunchtime. But the difference is you guys are here, whereas 2/3 of that class just doesn't show up. So today, rather than focusing in on a specific problem in the research that I work on, I'm going to present a general overview of the area of statistics on manifolds and how it applies to this area known as shape analysis to help give you an idea of some types of problems in statistics that people don't usually think of when they hear the term statistics, that I think really serve as the forefront of how statistics relates to mathematics, computer science, and other disciplines as well. So before I begin, I'd like to first just thank the organizers for inviting me to give a talk here today. As was noted, many of my students have been from Sri Lanka, and they've been telling me over the years how great of a country it is, how beautiful it is, and so far it's more than living up to the reputation of what they sold me as. Of course, in particular, I'd like to thank Dr. Krasgamage for inviting me to come here and for all the help he's done for helping me get over here. And I'd also just like to acknowledge the various collaborators I've been working on over the past many years on projects related to shape analysis. As you can see, many of the names here are Sri Lankan. All those from Texas Tech University are my current or just previous PhD students. So I want to start by talking about a few different problems that we could be interested in looking at where we can see shape information popping up to help solve problems in different areas. So the first one is, suppose we have contours or outlines of various different objects. Well, each of us can look at those outlines and visually tell that some of them are hand gestures and different hand gestures, some of them are fish, different types of fish, and one of them is a dog. How can we get a computer to distinguish those for us automatically? And this is really important in areas of computer vision as more emphasis is placed upon for security, trying to distinguish between different types of objects, and for artificial intelligence, trying to, again, also distinguish between these objects. Similarly, I have some protein binding sites here. Both of these are parts of proteins that were shown earlier, just the places where we know that there's binding activity that occurs to a chemical known as heme. And here what we want to try to figure out is, since we know they both bind to the same chemical, what atoms are actually common to both of these molecules that allow that binding activity to occur? And furthermore, once we've identified what atoms are actually in common, can we find any structural information that's common between them and analyze that in a statistical manner? So the underlying problem in both of those is we need to have a good definition of what shape actually is. Because we all have different ways we think about shapes as being. If you have kids, they probably think, oh, circle, square, rectangle, triangle, trapezoid. Well, maybe they don't know trapezoid, but we have these ideas. But there's a lot more information that can actually be contained inside of these configurations. Okay? And then once we have a way of defining what a shape is, we need to have a way that we can actually quantify differences between them so that we can perform a proper statistical and mathematical analysis. But before we can get to that, we also need to even know what we're looking at the shape of. So just to keep things as simple as I can today, I'm going to be focusing on configurations of points lying in a plane rather than three-dimensional configurations, which tend to make life a little bit more difficult. So these basic representations that we're going to be seeing here are known as k-ads, where a k-ad is just a set of k-ordered label points of interest that we call landmarks. Now, historically, these landmarks were chosen according to expert opinions. So for instance, for the stingray here, we could go to a biologist and get them to identify key points of interest on the outline of the stingray, such as what's shown in the middle image here on this screen. And we get basic information here, but we lose a lot of detail. But this was all really started around the middle of the 1980s, late 1970s even some. And back then, in order to do the computations involved with all these, they had to limit the number of points we had. But now we typically use higher level numbers of these landmarks inside of our representations, and we try to generate them automatically. So we get something that looks more like what we have on the right-hand side of the screen, where we have a lot more details present than what we originally had. And even today, now a lot of people try to work with these as the full functional representation so that we have all the details that we have on the left-hand side. Now, once we have these k-ads defined, we can now think about defining a type of shape. Now, there's many different types of shape. I'm going to be referring today just to one specific type known as similarity shape, which we say that two k-ads have the same shape if they differ by just a translation, rotation, and or scaling. So here, on the four figures that we show at the bottom of the screen, we can see that all four of these differ by only those three transformations. So they would all have the same shape. But we still have trouble mathematically trying to initially try to understand how that they actually do have the same shape, because they're all in different positions and have different translations and rotations. So we need to figure out a mathematical way of how to remove those effects to allow us to perform our statistical analysis. So one of the other things we need to do also here, big problem that pops up with this, is we need those landmarks to correspond to each other across configurations. So here, on the left-hand side, we've got an initial stingray where we start at the tail and then go in a clockwise fashion, labeling the points in successive order. Whereas on the right-hand one, we start at the front of the stingray and also go in a clockwise manner. But because of this, we don't have good correspondence here. So if any analysis we try to do based upon what we have right here is going to end up in something sort of nonsensical. If we ended up trying to say take an average shape here of these, we would get something that's a blob and really has no form to it whatsoever. So one of the things we need to make sure that we do in any sort of analysis like this is attain that correspondence. So here, fortunately, it's easy to just reorder them. But when you have a large number of landmarks, it becomes even more difficult to obtain these meaningful correspondences across configurations. But now, once we have those and have that taken care of, so for the rest of the talk I'm going to assume that that's the case, I'm going to start talking about how we can quantify the differences between these. Because it's a little bit more complicated than what we have normally. If we have two numbers, we know to quantify the difference. We can just go to our classical arithmetic operations and subtract to get a difference. But here, it's not going to be nearly as clear how we should go about doing this. So I'm going to start by talking briefly about a historical perspective on how people used to try to approach this process to more of the modern approach. And so you can see why some of these initial ideas don't necessarily work as well. So an initial approach is by using what's known as Bookstein coordinates to try to put all of our configurations in the same coordinate system. So the first thing we would do here is we place our first landmark, whatever we choose that to be, at the origin of our space. That removes any effective translation for us automatically. Then what we're going to want to try to do is place our second landmark, whatever we chose that to be, and place it on the positive x-axis. So now we've also removed any impacts of rotations, as we'll see in an example in a few slides. And then what we can do is once we've fixed those two transformations, we can now remove the effect of scaling by making sure that that line segment from landmark 1 to landmark 2 has a fixed length, say from 0, 0 to 1, 0. So now the entire configuration is going to be placed, both of these configurations are going to be placed in the same coordinate system, which we'll see what happens with that. So here we have two stingrays. They're not quite exactly the same here, as we'll see in a minute. But here what I'm going to do is I'm going to place these two different stingrays, which are clearly in different coordinate systems right now, into the same system based upon that approach. So here we've now placed them into those Bookstein coordinates. And notice here the 2 points right at the these 2 points at the origin and the second landmark right here, it seems like there's no variability right there. And that's because of the fact that we forced those 2 landmarks to be in the same place for both configurations. So the only variability is coming in from the remaining points. But now we've effectively removed those impacts of those translations, rotations, and scales. So now here, suppose we did that for a few more observations that we get here. Is now once we have them in this configuration, we can start thinking about doing more simple statistics. So before even thinking about quantifying differences, we can think about defining an average here. So now here we could just take our usual Euclidean mean, just add up the values of the coordinates and divide by the sample size at each one of the coordinates, and we can get an idea of a mean shape here. And that's exactly what I have right here. So now we can get an idea of what the average configuration of these shapes of these configurations of stingray points are. Okay? But that's great, but we actually can quickly see one problem that we can run into with this. So here's what happened if we used the 2 parts of the tail that I mentioned before, landmark 1 and landmark 2, as the points for which we standardize the coordinates. So let's suppose we change this a little bit, and now we use different points as our standardization criteria. Well, now we get different variability structures present in each of these other landmarks. As we go back and forth, we can see that this bottom set of cluster points down here corresponds to the top cluster points on the next slide. And we see that the covariance structure there is very different. And we see that it's true for every single cluster of these points. So we see that if we're going to then analyze the variability here, the variability is going to be greatly impacted by our choice of initialization, which is not so great because we might not have a really good reason for choosing the initial points that we did. However, once we have them in this situation, we can use classical multivariate analysis techniques to look at covariance matrices, perform principal component analysis, hypothesis tests, all the standard things very easily at this point. But the problem is, again, it's heavily dependent on our initial landmarks. Now, that's not always a bad thing. One of my other master's students worked on analyzing shapes of American baseball stadiums, which have the infields in common, but the dimensions of the rest of the field differ from stadium to stadium to stadium. So, because the infields or the inside of the park is all the same, that provided a nice criterion that we could use here. But in general, it's very difficult to choose that well. So instead we use what's known as procrastinators analysis sometimes. And this is based upon a Greek myth of about an innkeeper who only had one bed in his inn and wanted everybody to be able to stay in the inn. So what he did was if you were too short for the bed, he'd strap you down and stretch you out to make you fit. And if you were too tall, well, he'd strap the top part of you down and then cut off your ankles. Okay? So it's a little bit grisly, but it provides a nice way of viewing the shape analysis as we try to make the shapes match each other. So what we could do here is essentially solve a least squares problem. Here, I don't want to go into notation too much, but here we can represent these planar configurations in complex numbers, so we get a complex vector. And then what we do is we fix one of them, or we remove the center of mass from all of them. We subtract that from the coordinates so that to again remove the effect of translation. And to remove the effect of scaling, we divide by the length of that complex vector. And then all we have left to do is remove the impact of rotation. So what we can do here is simply fix one of them and try to find the optimal rotation to align the second shape onto the first one. So here, if we do that with the same data we just had, we get the configuration shown here. So as you see now, even here with the first two landmarks, we see variability present in both of them, in all of them now, because now no single landmark is in a fixed location. we're grouping them all together to find the optimal joint configurations or coordinate system here. So now that means that the correlation structures we see within each one of these landmarks are actually legitimate correlations. And so we have legitimate structure, not just imposed by arbitrary coordinate systems. And then likewise we can compare that to what we saw before. And we see it as a very different scenario. But now here, we're back to this, and now we can again get a mean very easily, the same type of way. And we can analyze the variability nicely for each individual landmark, but usually we're not interested in understanding that. We're interested in understanding the variability of the entire configuration, the entire shape. And that's where all of this is going to get more complicated. Because it turns out the space of these shapes is not a vector space, so it's not Euclidean data. Instead, it turns out that our space of shapes is actually a differentiable manifold. So the mathematicians in here are probably very familiar with that term. Everybody else, basically the idea is that locally it can be viewed as a flat space, but globally there's some curvature present in it. Classical examples are circles and spheres. It's why we can represent the map of, say, Sri Lanka very nicely on a flat piece of paper, but if we tried to take the entire globe and represent on a flat piece of paper, we're going to have distortions because there's the curvature of the Earth that we have to take into account. So, based upon that, now that we have an idea of physically what's going on, visually seeing how we change these shapes, it's helpful to think about what's actually going on geometrically behind the scenes. So this is one of the few places where I'm going to introduce some theory here to help I get this idea. But the main idea is our shape ends up not just being one configuration, but a set of all configurations that differ only by a rotation, translation, or scale. So we actually have an equivalence class. And that's why we get this curvature in our space. That makes life more difficult. And that curvature prevents us from just applying our usual Euclidean data analysis techniques, and even our general, which are all based upon classical arithmetic. We have to come up with alternative ways of going about doing this. But this approach that's used here dates back to 1984 from the idea of D.G. Kendall. And I don't want to go into too much detail about all these, but basically, to give you an example of what's going on with these, he focused in initially on the shape of triangles. Now, you'll see on the next slide, these triangles, some of them are going to be degenerate. So 2 points, 2 vertices of the triangle might actually be in the same point, or they may all be collinear. So not usually what we teach to children as being triangles, but we'll work with it here, okay? And we can see that it turns out that the shape space of these triangles is actually a sphere. So this is the one case where we can actually visualize what's going on in a shape space to understand how we can describe the variability and differences between these. So here is an image from a book by Dryden and Mardia. It's a part of the sphere. So here at the North Pole, we have an equilateral triangle with the orientation in going counterclockwise A, B, C. Okay, then the South Pole of the sphere, we're going to have a triangle, an equilateral triangle going in order, going in the other direction. So clockwise A, B, C. Okay, but now suppose we go along this one path here from the North Pole down to the equator of the sphere. Is we see that we get isosceles triangles, where the length of the segment from AC and BC are the same, are equal to each other. As we go down, we eventually see that C, we get one of those degenerate triangles, and it's right in between A and B. Now if we go along the equator in this direction, we see eventually that C will move to the same point as B, and then we can go back up and we can see different triangles in between. So this allows us now to identify each shape of a given triangle with a point on a sphere. So then, to quantify differences between these shapes of triangles, all we need to do is find differences, to find distances between points on the sphere. and that'll get the job done for us. Now, in general, there's two basic ways of trying to calculate distances between points on manifolds, whatever they are. One yields what's known as an intrinsic analysis, where we equip the manifold with what's known as a Riemannian distance, or a Riemannian structure of our choice. And a Riemannian structure is just an inner product defined locally. So that then provides a distance for us that we can use directly on the surface of our manifold. Another approach is to use what's known as an intrinsic analysis, where we embed our manifold into a higher dimensional Euclidean space and take the distance from that. So I'll show an example of what I mean by each of these on the next slide. So here, an example I'm going to be coming back to pretty frequently here for the rest of the talk is directional data analysis. So see here we have 2 points, one is at 10 degrees and one is at 350 degrees. If we want to calculate the distance between them, there's two basic ways we can do this. We can first use an extrinsic distance, which on a circle means that we're taking the length of the chord connecting them. Now, here we're not directly using the circular structure of the data. We're just saying, okay, these are 2 points here in a plane. So the shortest path between any 2 points on a plane is a straight line. So we just take that straight line distance. But the other approach we can take here is to travel along the path of the circle itself and travel along this curved path, which yields an intrinsic distance. And here, that's the arc distance. So the length of the arc that we travel along. Okay? Now, these same ideas hold true for more complicated, more abstract spaces, for the other types of shape spaces that we'd be dealing with. And this is the main philosophical breakpoint in this area of which type of distance do you use. And some people are very dogmatic about which one they want to use. I tend to take the approach of which one helps us solve the problem that we want to solve the best. But then once we have these distances defined, we can use the two general classes of statistical analysis. Initially, there was a focus on parametric analysis. Just as with any type of statistical situation, you try to put probability distributions on your data to help you model the observations and help you understand what's going on and draw conclusions. But the problem with this is, even though they're very easy to use, as with any probability distribution, unlike classical Euclidean data, we don't have general goodness of fit tests. So we don't know how well these probability distributions actually model our data, which is problematic. So with advances in technology and computational power, most researchers in this field have switched over to focusing on non-parametric procedures, where we typically use asymptotic theory, so central limit theorems, or resampling techniques such as bootstrapping or permutation tests to perform our statistical analysis, to draw conclusions. But now there's still a little bit of a push to go back in the parametric direction, because even though we have the computational power to handle simple data sets now for the non-parametric scenario, a lot of times now we have so much data, it again becomes computationally prohibitive to actually utilize these computationally costly procedures. So one classical thing that statisticians are typically interested in are defining location parameters of a probability distribution to understand where are the data bunched around, to understand what are typical values. Now, for parametric models, you can use maximum likelihood estimators to find your location parameters, just as you would in Euclidean case. But in a non-parametric setting, we can't just define our mean to be the expected value of x, because that's going to depend, our answer is going to depend greatly upon our coordinate system. So again, we get back to this problem of coordinate systems interfering with the analysis. So instead, what we do is we utilize what's known as a Frechet mean, which dates back to the 1940s, I believe. Frechet came up with this idea in other contexts. But we take the idea that the mean is a minimizer of the expected squared distance between points on the manifold on our space and our random object. And now our usual means that we talk about in any other context have this property. So it generalizes nicely from our usual idea. But this will allow us to work with things very nicely. But now here, the main thing I want to point out here is this mean depends upon the distance we choose. So in general, if we choose different distances, we're going to get different means. But to illustrate why this is an important idea, that we can't just use expected value of x by itself, I want to go back to this directional data analysis example, where here we have these two observations, 10 and 350 again. So if we use our usual definition of a mean here, we would just take 10 plus 350 divided by 2 and get an average of 180. But that should be pretty clear. It should be pretty clear that that's problematic, because that doesn't describe where the data is located at all, because it's on the polar opposite side of the circle from the other two observations. But now suppose we change our coordinate system just a little bit. So suppose we change where the 0 is. But we still have the same two observations, but now, because of the change of the coordinate system, we take 20 plus 40 and divide by 2 and we get 30 degrees, which is a much more sensible location of where we would think the mean would actually be here. So in this case, we get something intuitive. The previous case, we don't. So we want to avoid that scenario entirely and define, if we use that idea of a Frechet mean here, in both scenarios, the mean would end up being in exactly the same place. So here we get that Frechet mean. Okay? So, and because this is the point that minimizes the squared distances to the other observations. Now in this case, because the data is so concentrated together and it's only two observations, we actually would get the same mean here, regardless of whether we use the chord distance or the arc distance. But in general, you're not going to get the same means. So I want to show that, to illustrate that, I want to go to this quick example here with wind directional data, where here we have data observations. It might be a little bit difficult to see here, unfortunately. Blue points mainly around the equator of this sphere. So it's just showing where the wind came from in different or wind was blowing in different directions. So now here we see it covers pretty much most of the width or most of the circumference of this sphere. So then here, if we take another look at this and we compute the intrinsic mean and the extrinsic mean, means with respect to those different distances, here we see in red we have our extrinsic mean, the one calculated using chord distances, and in green we see the one that's calculated using those arc distances. And we see that one actually ends up getting pulled down a little bit, which is kind of counterintuitive initially, because we don't have any points going down that way. But the reason for it is because we have points on the opposite side of the sphere that serve that the easiest way to get to those is by going down under the south pole of this sphere, much like the way that planes travel long distances. To go from, say, Dallas, Texas to London, for instance, you actually go well north of just going that approach. The same thing happens here. Okay? And now here, just to pull this back to shape analysis a little bit, to get back to this motivating example, we can then have some configurations of this hand gesture here. And if we take these hand gestures and apply these ideas here, we can now get an idea of a mean shape that captures the overall pattern that's present in all four of these configurations. Okay? Now, going further back to the original problem, with distinguishing between objects is based upon ideas of means and also all these distances I've been talking about. It provides a way of quantifying these. But now statistics beyond the mean become considerably more difficult to talk about, and you have to get into a lot of technical issues that I knew I wasn't going to have time to talk about. But basically the main idea is, the reason it's called a differential geometry that we use here, do this is because we can find a space that's tangent to our manifold at any given point. Much like at any point on a line, on any function, or any differentiable function, we can find a line that's tangent to it. We can do the same thing here. So on a circle, it's a line. On a sphere, it's a plane, and so forth. And then what we can do is we can project our points to that tangent space and perform a statistical analysis there. Talk about the variability in that tangent space, on the points projected to that tangent space. So that allows us to identify and define well ideas of covariance matrices, confidence regions, test statistics, and perform principal component analysis. And a typo from when I was working on this late at night, which I shouldn't have been doing. Okay, and regression. And regression itself is a very new idea in this area because it's not a straightforward generalization from our normal ideas to these non-Euclidean scenario. Okay. So here I wanted to just provide some key references. The Kendall's pioneering 1984 paper, and then 3 books, including one that I co-authored that came out 2 years ago, that are the main large pieces of literature on this area of shape analysis and statistics on manifolds, in case you ever want to know anything else about them. Okay. And there's not too many places across the entire world that have concentrations of faculty working in this area. It's growing increasingly year by year, the number of institutions that focus on this. So it's a growing area, but it's still relatively small. So I just wanted to present a basic idea of all this to you guys here. So if nothing else, if you ever encounter this, you have some idea of what's going on with this. So that is the conclusion of my talk, and thank you for listening.